values of K and W?
Right, so that spring constant of K is 5 newtons per millimeter. And since they tell us W is 100, we'll include it in the given. Again, if we use it again somewhere else, like in the diagram, if it shows up again, it's not a big deal. But that way we remember it later when we're trying to draw from this information. So in this problem, what are we trying to find, both kind of conceptually and then as a mathematical object, what are we trying to find? Right, we're trying to find this delta. So when we put this crate on the incline and let it go, and eventually it comes to equilibrium, meaning the velocity is 0, its acceleration is 0, we want to know how much did it deform, how much is that spring stretched or compressed from its original length. So again, that's what delta is. It's the change in length of a spring. It's not the final length of the spring, that's L prime, and it's not the original length, that's L naught. And that's all we're asked to find in this problem. So we know that in our equation step, we better have something that has delta in it before we're declaring ourselves done. So let's draw our free body diagram here. So what point or what object can we treat as the particle that all the forces are going to act on? Right, so the crate or this cart, we can reduce down to a single particle that we want to analyze. Right, so this is our cart, our simplified cart, and there's no coordinate system given, so we can establish our own. So our old favorite, x right, y up. And also helpful to us, or a helpful construction line to have here, anytime we have a surface that we're dealing with, it's usually a good idea to add that surface as a construction line, since we're probably going to have things parallel and or perpendicular to it. So we know that we have this surface that is 20 degrees from the horizontal, from the negative x horizontal. Right, so we have to have our axes. This construction line just helps us out in the next steps. All right, so what are the forces that are acting on this crate? Yeah.
You have the weight and the straight down, which is 100.
Right, so the weight, we're going to say that gravity acts always in the negative y direction. So they told us that the weight was 100 newtons. That's already a weight force. We don't have to, in this case, multiply it by gravity. It's already good. Yeah.
And then you have the force of the spring holding the cart up.
Right, so
Restricting it.
right, so a little bit more detail on that. So, right, there's going to be a force from the spring. What is the direction of this spring force? Yeah.
Up into the left.
Right, so it's along, the way that the picture has it, it's along that 20-degree incline. So I'm going to make the assumption of tension, because that's how the equations work. You could assume compression if you wanted to. But I'm going to assume it's in tension, so it's pulling on this crate. And I'm going to call the force in that spring F sub k. So I like this convention of spring forces having this k subscript, because it's going to remind us later in our equation step, oh yeah, that's not just some force from someone pushing it, that's a force specifically from a spring. So it's a good kind of mnemonic device, like how T for tension, you know that it should be positive. All right, and then what other forces or force acts on this? Yeah.
Normal force.
Right, so the force that keeps it from falling through the surface, that normal force. So in the picture, how do we represent the normal force? Perpendicular to, right, this 20-degree line. Normal forces are always perpendicular to the surface. So to this 20-degree line, right, that's where we have this normal force. So we know it's orthogonal to that line. So we could put its real direct, or more information two different ways. We know that if this is 20 degrees from the horizontal, then this is 20 degrees from the vertical. Or if you prefer always working from the horizontal, you could say that that's a 70-degree angle. That would be perfectly fine. But the important thing is it's perpendicular to this 20-degree construction line. Oh, and also the normal force, not only is it perpendicular to the surface, but a normal force can only push on objects. A normal force can never pull. So if we found out that the normal force is negative, either equilibrium is not possible, or we made a mistake in the modeling, or we made a mistake in the mathematics of it. So normal force is, oh, and I'll name it N for normal force here. Normal forces must be positive, otherwise we did something wrong. And that's always true, just like ropes have to be in tension. Okay. Questions, comments on the free body diagram step? Yeah.
What if the surface is a solid surface? Something flips on it.
Oh, if it's, in this class, everything we look at is a rigid body, so there's no deformation, except for a spring. But all surfaces and all like rods and members like that cannot deform. In 213, then we'll get into deformable surfaces, in which case, right, you do have to compensate for, if it's on like a spongy surface, it could kind of sink into it a little bit. And then, right, the normal force is not necessarily it's not necessarily in the positive y direction. It'll always be perpendicular to the surface itself. So yeah, it could get complicated if there's like a divot there, because then the normal force is going to be in all directions. So we'll save that for later. Okay. Other questions on the free body diagram? All right, so we use the free body diagram again to make our equilibrium equations come from the free body diagram. So if we look in the x direction, according to our free body diagram here, we have that spring force pointing to the left, so negative Fk cosine 20. The weight force is in the y, so it does not count. And then the normal force, the horizontal component, points to the right. So normal force is going to be positive. And I'm going to use 20 degrees here. So if I want to use this 20-degree angle, the horizontal component of the normal force is opposite. So it's going to be n sine 20. Sine 20, cosine 70 are exactly the same. So no matter which angle you use, as long as you realize that it has to be perpendicular to that 20-degree line, sine 20 or cosine 70, same thing. In the y direction, now I have my weight force down. So negative 100 newtons. My vertical component of the spring force is positive, and the vertical component of my normal force, which will be cosine 20, also positive. Right, so these are the only equilibrium equations we can draw, that we can draw from our free body diagram. So two equations. If we look at, we actually only have two unknowns here. So one option would be, right away we have a solvable system. Let's jump to the solve step and find n and find fk, and that's fine, but we want to realize that we're not done until we've found what is in the find step, which is delta. So we have two equations that it's a solvable system, but neither of them have delta in it. So we will need more equations. One of them must include delta, otherwise there's no way to find its value. So the order you do these steps in is not crucial. I'm going to present it doing all the equations and all the solve, but if you wanted to do the solve right now and then come back to more equations, that's also fine. But we know we need at least one more equation, and that equation that has delta in it. So what information have we not used yet at all? Yeah.
Would it be negative like 2 Fk because it has the 2K?
Right, so this spring has a spring constant of 2 times k, right, and they told us k was 5. So for the spring, its spring constant, right, is going to be 10. But what equation do we need in here? Yeah. Right, so this is where we use Hooke's law. So far, nothing here is revealed that it's a spring. So this will say, well, that force in the spring is going to be that k. I'm going to put in quotes right now because we already used the letter k to mean 5. This is the spring constant of that spring times the deformation of the spring. Or it'll be k times L prime minus L naught, both of which are okay. But we don't know either of these, and we don't care for this problem. We just need to find delta. So I'm only going to use this version of it. Again, this is the actual spring constant of the spring. And if you look at the picture, it tells you the spring constant is 2 times k. So this is going to be 10 newtons per millimeter, because it's 2 times the k that we wrote up there. So if we look at equation 3, so this is just Hooke's law here, we've introduced one more unknown and one more equation. Fk is an unknown, but it's not a new unknown. It appeared in all of our previous equations also. So in this system, we have 3 equations and 3 unique unknowns. So we, again, have a solvable system, and we now have an equation with delta, which is what we ultimately were asked to find.
Do you need to note anywhere in your free body diagram or in the given that your constant is 10 rather than...
Right. Yeah. To be fair, we should have put that somewhere, maybe in the given, that the k was 10, because really, right, without that picture, it doesn't really make sense where this comes from.
Yeah, okay.
So there's a little bit of artistic license here of what some things you can leave out of the problem. Right. So we could have said that this k was really 2 times k. All right, so now we're ready. Yeah.
Do we need the equation for normal force?
The equation for the normal force.
Calculate normal force based off the weight.
Normal force is based on here. So one thing, if you're thinking of what you did in Physics 211, normal force is not equal to weight, except in very certain circumstances. The normal force can be greater than the weight. It can be less than the weight. We always solve it because it appears in equilibrium equations. So we don't have to make any assumptions about the value of the normal force. We're going to be able to find it once we solve simultaneously. So the only time that normal force is equal to weight is when something is resting on a horizontal surface, which we sometimes see. But in this case, when we go to our solve step, so if we solve equations 1 and 2 first, we're going to get that normal force is not equal to the weight. Rather, it is equal to, where did it go? 94 newtons. All right, so the weight is 100. The normal force is less than that. It's only 94. And the force in the spring, Fk, is 34.2. Yeah.
Since we're only solving for delta, do we need to still solve for normal force?
You kind of, if you're solving by hand, it's inevitable that you would have to solve for Fk and n simultaneously. I guess if you did a substitution for n, you wouldn't have to find n to be able to find the delta, right? So we don't need to find n, but normally you probably would along the way anyway. But yeah, if you don't, that's fine, because all we care about is delta for this one. So using equations 1 and 2, we find this, and it also could be a good check along the way. In this case, it's not a big deal because the spring force could be positive or negative. This tells us that the spring is in tension, which springs could be in tension or compression. We made the assumption of tension, but it didn't have to be. One thing, finding that normal force is a good idea here. Again, it's a kind of a check. The normal force must be positive, or we did something wrong, either in the math or in the modeling. It is positive here, so that's kind of an intermediary check we can use. So positive normal force, that's a good sign. Using equations 1 and 2, pop that into equation 3, and now we can find that delta, if I'm measuring this in newtons per millimeter, the deformation of the spring is positive, which if it's in tension it has to be, is 3.42 millimeters. And if you want to express this in base units, 3.42 times 10 to the negative third meters, either which it would be acceptable